Thanks a lot. Thanks for the introduction, Maurice. And indeed, I think it's very nice that Monica ended her presentation with the establishment of the focus group by Senelec. And indeed, like Maurice says, I am the chair of this focus group. Personally, I am, as you see, affiliated with university. I'm in academia. I am a developer of organ-on-chip technology. And for me, definitely standards is a key aspect, I think, also of our dissemination. So Monica mentioned that for a lot of scientists, it may be a little bit of an afterthought. For me, it's really an integral aspect, I think, of doing our work. So very briefly, I wanted to talk about two aspects basically in this talk, very briefly about standards, because it was already nicely introduced, I think, by Monica, but also afterwards about open technology. I showed this figure. This is a figure from a European project called ORCID, Organ-on-Chip in Development. If you want to know more about that project, you can check out the website there. The project has ended, but the key output actually of this project was the establishment of the European Organ-on-Chip Society. And I took this figure from one of the reports of this ORCID consortium, in which a roadmap is given, as you see from the left-hand side, initial development all the way to implementation application of organ-on-chip technology, and what are the key aspects and steps along the way. And standardization obviously is one of those key steps that was identified by this broad consortium. And well, again, Monica has introduced all the efforts currently underway in Europe when it comes to standardization in organs on chips. If you would like more information about this focus group, and I think also it's good to clarify that a focus group is something different from a technical committee. That's something I realize already quite often, that people think that we're already developing key standards for organs on chips. That's not what this focus group is about. It is about finding priority, timing, synergy with ongoing activities. As Monica very nicely mentioned, of course, there's so much already going on in this domain. So we try and involve all stakeholders in this focus group to identify in the coming year and a half, where to take action as soon as possible. And the nice thing, of course, is that we do this now in the context of Sen and Senelec. So we have also their listening ear, they're watching closely. How can they help us and support us? And where is the first steps that we need to be taking for standardization in organ on chip? If you feel that you, like I just listed, let's say a random group or word cloud here, but if you have opinions or you think you have a strong opinion, something to say about some of these aspects, definitely this is an open focus group. So feel free to just go to that website, reach out, and become part also of this initiative. Okay, so like I said, I wanted to only touch very briefly on that standards aspect, because I wanted to highlight something else from this same figure that I showed before. And that's also the aspect that I mentioned in the title, and that is the importance for open technology platforms that was highlighted and acknowledged by this European consortium. And I wanted to sort of educate you a bit. And of course, it's very, let's say, very much intertwined, I would say, with standards and standardization, but maybe it'd be good to learn something about open technology platforms. So if we're going to be talking about what a platform is, or what what open technology platforms are, then we start maybe with the definition of a platform. And I think this is important because we throw this term out a lot, saying like, yeah, we are all working on organ-on-chip platforms. But like, if we make it explicit, then a platform, it comprises a set of components with shared interfacing rules, from which you can, by combining them and interfacing them, build higher level applications. So this is, of course, a very broad definition of a platform, but this is what we're talking about. And I think another very important aspect of standard of platforms is that it always includes multiple parties coming together, right? So typically you could define the roles that are important in the definition and use of a platform into these groups. So users, developers, manufacturers of components of that platform, and then that final category, sponsors, is basically a term that defines groups of people, stakeholders, that define the interfacing rules. the components, like what is actually what are the components that make up this platform. So they don't necessarily need to just produce anything, but they have a very strong say in what that platform should look like. And the interaction between these groups can take multiple forms. And I just plotted, let's say, visually 2 ways of how these groups can come together to define a platform, right? And on the left-hand side, we see, I think, a very collaborative way. All these groups come together and actually together define something that then in the end becomes the platform. But what we see quite often, of course, is that there's one party, as we see on the right-hand side, that maybe has the role or integrates all the aspects of the platform developer, the platform sponsor, manufacturer. So they define actually what all the components will look like, and then just make this available to users and listen to users what they would like to get out of it. So this is just, let's say, a framework of thinking a bit about these platforms. And then it's going to be important if we then transition into thinking about open platform technology in a minute. So if we think about platform technology and apply that more to this domain of organs on chips, so I just try to outline it a little bit more general, but if we now apply this to organs on chips, then it's clear that maybe in a very implicit way, we are, of course, very much used to thinking about platforms in organs on chips. And what is interesting there is that stems also from a certain need, right? So on the one hand, you have people that are using organ on chips systems, and they are focused on certain functionality, getting physiologically relevant systems that are easy to use. But on the other hand, of course, we have developers and engineers, scientists developing new organs on chips. And for them, it's important that the systems that they're working with are flexible in the sense that you can integrate new functionality, that you can maybe just replace components and tweak the system to fit the new purposes that are demanded by users. So thinking about the field of organ on chip and thinking about the role of platforms there is that it stems from this very strong need for ease of use as well as flexibility. And this is, of course, where let's say a system that consists of components that come together via interfacing will actually give that power. So to make that maybe slightly more concrete, so we actually have quite a few examples, and I just listed 3 random companies here, and we see a lot more actually in the meeting this week that have made their own organ-on-chip platforms and designed it. And these are all proprietary platforms that I'm showing here on the slide. And typically, we can identify key components of such a platform. For example, here, like working our way down the columns from left to right, is that typically you have chips, and those chips go into sort of like holders, and the holders then can be clicked into a system, etc. Right? So this is a very, again, like a modular component-driven way of building your platform. And all of these aspects, of course, then require certain ways of interfacing. So I think this is typical, of course, what we see here with these proprietary organ-on-chip platforms is typical for what I showed you just before, is that these platforms, in a way, they are very much open for users. And like these are companies, so yeah, users are their customers. And of course, like they will work hard to make these products usable and accessible for their customers, for their users, make sure that it fits the needs of these users, etc. But they are very much closed, of course, for external developers, manufacturers, or sponsors. All of that, of course, is just kept in-house by that company, and they decide what the platform will actually look like. So that comes, of course, or brings certain challenges. So that means that whenever we pick a component from one of these proprietary platforms, and again, I just show an example here of an emulate chip, and then try and combine that with some holder or component from a tissue system, of course, there is not going to be any interchangeability. Like this was never designed to actually interface in that manner. And this is something, as a developer or more an academic developer, something that we run into, of course, a lot, is that if we are developing or designing our own organ-on-chip devices as a component in the laboratory, then it is not very simple, of course, to take that component and integrate it into the platform that is already out there into one of these proprietary closed platforms. And I show here an organ-on-chip device, but we interact, for example, a lot with either groups that work on sensor technology or companies that work on micropump technology, and they really would like to help out and make their products available for users of organ-on-chip systems. But it's not easy for them because they just need to somehow manage to find their way into these closed platforms. And that typically only works by working directly with that company and trying to convince them that you have a key component that will make their platform stronger. So none of that, of course, facilitates actually the participation of new developers, new manufacturers of these platform components. So this is why we actually have a need in this field, particularly if we focus also on innovation and making sure that actually we have quick exponential growth of working off of each other's innovations. We need these open platforms. And I believe very strongly that that will then speed up also development of next generation organ-on-chip systems. And this is also why we focus at the University of Twente, but also within bigger consortia like the National Organ-on-Chip Consortium, HDMT in the Netherlands, on open platform technology. And I'll show you a very, let's say, short movie like that illustrates the problem or challenge that I just gave you, right? Like, so what if we have developed a new organ-on-chip device and we cannot really go and immediately fit them into one of the closed platforms? And then this should be, unfortunately, all too familiar for a lot of developers here in the audience. We end up with systems that sort of look like this, right? Like big spaghetti of tubing, all the bubble trouble that comes along with it. So we really need to try and fix this. And this is why we focus on this open technology platform called TOP. And central to TOP is actually what we are seeing there on that microscope slide. And what we see there, that white rectangle, is the fluidic circuit board. So this is something with the exact footprint and dimensions of a microtite or a microwell plate, but it actually contains all sorts of microfluidic channels and thereby provides also a standardized interface for new organ-on-chip devices. And the interfacing rules for how you can actually click devices into these slots that are highlighted here, those interfacing rules are based on ISO documentation. So this is something that you can just find. You can find what is the inlet diameter, what is the inlet pitch, etc. Like all of that is out there, and you can just design your component so that it becomes automatically compatible with such a fluidic circuit board and with this translational organ-on-chip platform. So we have quite a few of these projects actually going on applying this platform, right? So for example, there are people in the audience here, Anke and Eric, they helped yesterday also with the educational workshop. They're working, for example, on integrating multiple chips from multiple technical universities in the Netherlands, and then also new university medical centers in the Netherlands to all fit into this open platform. But I just wanted to show you one more, let's say, internal example of how we are applying this platform. And that is via this example of this heart-on-chip device that we developed in our lab. So the exact details of this heart-on-chip device, of course, are not like really important in this particular talk, but it's a very, let's say, typical organ-on-chip in the sense that there's an open-top microcompartment, a row of microcompartments containing cardiac tissues. Then there's a porous membrane, and then there's a microchannel running underneath that is used then as, let's say, the vascular compartment. So we've all seen Don's talk yesterday. It's very reminiscent, I would say, of the long-on-chip layout. This is then, if we look from the top, we see that we can culture endothelial cells in that vascular compartment, and we can culture three-dimensional cardiac tissues in that top compartment with a certain geometry. And then I think this is a more like clear view with bright field microscopy. So we see a beating cardiac tissue there, separated by the vascular or from the vascular channel by this porous membrane. So actually, in this project, when working with these devices, we ended up at what you just saw schematically or via artist impression in the movie, right? We ended up with a system, and again, this should be all too familiar for a lot of people in the audience. Huge system sitting in the incubator, lots of tubing connections, this whole spaghetti of tubing going on here just to interface with that single chip sitting here in the middle in a Petri dish. And we decided to use this, let's say, organ-on-chip device as a use case for can we integrate this in such a translational organ-on-chip platform? Can we click it in a fluidic circuit board and then use that to actually drive flow through the vascular compartment? So this is the end result of what, let's say, that project looks like. And it's also summarized in that lab on a chip paper that is referenced in the bottom. And I just wanted to just give you a glance of what we designed there. So here we see an example of a fluidic circuit board in pink. So it has that Welsh plate footprint. It has the interfacing rules that are laid out in the ISO documentation. And we have multiple components interfacing with each other via this fluidic circuit board, both at the top, and you can hardly see that, but actually the heart-on-chip device is sitting at the bottom. And if you would like to see this, then I think this, at least this particular fluidic circuit board is still somewhere in probably Eric's hotel room right now. So you'd have to go and try and find him, but he can show it to you. So the components at the top, they are not things that we developed in-house. They are commercially available components that we just interfaced with each other via these standardized interfacing rules. So they are solenoid valves for switching the flow from one route to another. They are a commercially available flow sensor. They are commercially available glass reservoirs, etc. None of these vendors, of course, knew that we were going to integrate this in the system, but that was also not necessary. We just knew that these components actually fit the right standards that we wanted to interface with each other via this platform. So that brings me basically to this wrap-up slide and saying like, okay, and the top is that open platform. And I want to clarify one thing there is that whenever I talk about open platform technology, people always tend to, the first thing to go to in their mind is to say, oh, so that's sort of like open source. So probably everything has to be free. So it's going to be more, let's say, only for the academic community or so. But I want to stress that an open platform means that it opens and welcomes participation, right? So this is what we do with this fluidic circuit board. We, as University of Twente, we innovate this fluidic circuit board, and all the design rules are based and out on freely available ISO documentation. But if you come in as a industrial partner and you have a beautiful building block, a flow sensor or a micro pump that you want to have interfaced with this platform, then it's not necessary for you to also subscribe to this whole open philosophy. You can keep your building block closed as long as you follow the right interfacing rules. It will just connect and click into this platform seamlessly. So this is something I think is important to keep in mind. Then I don't know if our timer is, but I wanted to like maybe in the last 2 minutes show a bit also that we are basically continuously developing this platform as well, right? So what I just showed you, that example with heart-on-chip, is actually a relatively straightforward fluidic circuit board, and like with just some micro channels connecting each other, but it serves as a nice example. But we are actually focused on making this platform extremely powerful. And one way to do that is by promoting automation and multiplexing. And we do that by making a use of what is known in the field of microfluidics as Quake-style pneumatic valves. And so it's developed by the lab of Stephen Quake. He was the innovator or the inventor and pioneer of this element. And it's a very simple element, right? It's just a way of automatically opening and closing microfluidic channels as depicted there. So an open state, and then you pressurize a green channel, and then a closed state of the flow path. And we are using this to make multiplex devices with, in this case, 64 individually addressable microfluidic chambers for cell culture. And then we put these types of chips on these fluidic circuit boards that I just showed you. And inside the fluidic circuit board, you make use of these same automated pneumatic valves. And then this is basically the end result of something like that. So we have here 3 of these multiplex chips. So in total, 192 individual microfluidic cell culture chambers. And as you see on the far right-hand side, there is the pneumatic tubing coming in that controls all the flow to each of these individual flow chambers, and also decides which of these chips are being addressed at that particular moment in time. And as we see now with the final chip, we actually have that down to the resolution of a single microfluidic flow chamber there. Like, so every culture chamber can be addressed individually here. And this way of automating the cell culture can actually be quite powerful. So we, for example, do stem cell culture in there, stem cell differentiation. On some of these protocols take multiple days, up to 15 days in this case, where we see that in the end, we got human pluripotent stem cells to express NKX 2.5, a cardiac marker, and actually contract in these systems. And none of this actually needed any intervention of the researcher. This is all handled by the automated system. So it really goes to show that this is going to be a very powerful platform also for you. So in the end, I want to thank a long list of people at the University of Twente who are collaborating to make this platform a success. Then also within HDMT in the Netherlands, we are working very hard and now actually trying to spin this out a bit also towards the European community. I highlighted the names of the people that are also in this meeting, so go and find them if you want more information also about this platform. And with that, I'd like to thank you for your attention.
Thanks so much, Andries. That was a great example of utilizing existing standards, being simply aware of them and then using them, and then also putting, new science into new standards. We got time for one question, Ivan.
So thank you, Andries. It's a very interesting proposal, albeit as a person who's seen probably 30 different configurations of chips, I can tell you that maybe 3, as the ones that you showed, will actually fit into your open platform and 27 will not. But that's beside the point. What I wanted to ask you is, we have a lot to learn from, again, genomics. I hate to bring it up, but that has been the previous wave, at least, that some of us tried to catch, right, unsuccessfully. So, and standardization of that technology was on data. MAQC, Microarray Quality Consortium, was on data, not on platform. There were, everyone was making their chips, just like chips here. Then there were 2 companies, now there's only 1. And no one is talking about standardizing technology. Everybody's talking about standardizing the data. So how would you consider an answer in the MPS world to that?
Yeah, so it's a very good question or comment, I would say. So when it comes to the standardization of data, for me, this is a key component of the effort I talked about in the first place, like the focus group standardization organ on chip. This is definitely an aspect we need to address there. It's not, however, the only aspect that standardization can have an impact. And that's the point I try to make, of course, with the open technology platforms. The way I see this or believe this is that we are actually at a relatively early point in the field of microphysiological systems or organs on chips. So we see devices, but all these devices, I think 10 or 15 years from now, we'll look back and think that was actually very rudimentary basic technology. In the end, actually, all of these systems, if we can integrate components from all the great minds in this audience into single platforms, that's actually where we will get technology, organ-on-chip systems with levels of functionality that we currently can hardly imagine. So I think really this is, let's say, me being maybe a bit of an optimist there, or maybe just thinking that I need also a job 10 years down the line as a developer. But this is really what I believe is that, just a chip with 2 compartments is probably not the endpoint for the field of MPS.
That's great. Okay, thanks, Andries. Hopefully we'll have some more time at the, is it quick?
2 quick questions. Claudia Gärtner from Chip Shop. So we are a manufacturer of whatever plastic or glass components you need for microfluidics, or be it organ on chip. 2 questions to you. I like the approach. We discussed this 20 years ago also with the microfluidics. First of all, how do the manufacturer come into play? Because when I look at your devices, you still have a lot of components you add. What could be for free if you do it in a manufacturing way. So interfaces and things like this would come into play for free. And the other thing, what I see, it looks a little bit electronic dominated, and you nicely made the reference. But when we look in the microfluidics world, I would always look more on the SPS and microtiter plate and slide world. So this question, first of all, how manufacturer and why does it look so electronic-like?
Yeah, so I think the latter, is maybe just a matter of taste and well, not so much to maybe go into, but you're definitely right when it comes about manufacturing. That's an element that I didn't really stress here, but I did mention, of course, manufacturers as one of the parties that actually comes together when it comes to designing or using platforms. And also in this case, so some of these fluidic circuit boards for prototyping, for example, we make them in-house simply by doing PMMA, micromilling and things like this. But at some point we feel that, okay, this is actually at the point that we are going to use it and widely use it or need it. then we just go to local companies, like a company like Micronit, and just order, like a couple of boxes of these plates. This is, let's say, I think, again, the point that I'm trying to make here is that this should also be open for manufacturers, right? So if, the competitors of Micronit say, well, I actually can make this a lot better or cheaper, then it should be open for them to actually do so. This is at least, the vision or the philosophy that we will follow.